Hello, today we're going to talk about Stokes' theorem. So Stokes' theorem is a generalization of Green's theorem but in 3 dimensions, not 2. Okay, so what do we mean by this? Let's write down what Green's theorem was again. So Green's theorem was we have some vector field which is defined in 2D. P and Q are the 2 components of this vector field, and they're both functions of x and y. And we have some closed loop, and we think of it as a simple loop, so just something like this, like that, and it's going around like so. And it encloses some region D. Okay, so we have a C, which is our closed loop, and it encloses some region D. And we assume then that F has continuous partial derivatives in P and Q, and that this is a simple loop. It has no crossings. It doesn't loop around twice or anything like that. Then we know that the work integral of pushing some particle through the force field, or this vector field, and computing the work over the distance of that path, C, is equal to the enclosed area integral involving the partial derivatives of Q with respect to x minus the partial of P with respect to y, dA. So again, this has to be continuous inside of here, and it has to exist for everything inside this flat region. So again, this is in, we think of that as an x and y, right? Like so. And then this works out just perfectly. So now, what do we talk when we talk about Stokes? What we want to do then is first we're going to have to bring this up to 3 dimensions. So just a little utility here. We have to define our vector field as such. So our vector field now will be 3-dimensional. And again, we have some closed loop. Just like before. But now when we write it down, we're going to write down a work integral. So now what we're going to do is I'm going to put a 3rd dimension on this Z, and I'm going to put a surface. So now C is embedded somewhere in 2D. It doesn't have to be in the plane, XY plane. So it can be like this. There'll be some surface that's enclosed inside this region. So we can think of, I'm going to just make a little dotted line there to indicate that's the back side there. All right, and so we have some surface that's filling out the boundary of that surface then is connected to our path C, which is still counterclockwise oriented. Again, this is counterclockwise. Same thing here, counterclockwise. But what do we mean by counterclockwise now in 3D? We have to, so what do we mean by counterclockwise? We have to, because of course if my eyeball is down here, there's my eyelashes there, if I'm looking up on that, this would be clockwise. But if I'm looking down on it here, there's my eyeball, it looks counterclockwise, like we want. So what we have to do is have a notion that the surface, which we'll call S, is orientable. Which means that we can define a normal vector that points outward from it, and there's no ambiguity about which side we're on. It means that it has 2 distinct sides. So once we decide on a convention of which way, so here's our normal vector sticking out of there. Once we decide on an orientation, which is the top and bottom, so we say top and a bottom. Once we figure out which one we're talking about, so if I'm looking down on it, we assume that the surface that we're looking at, we'll call that the top or the outside of it. in which case then the orientation we want to take our path will go around this way. But if I was going to take the inside of this surface, which looks a little like a butterfly net or some sort of dome shape, if I was going to look up on it this way, I would pick the other orientation. I would think of the inside as being the top. Either way, we just have to decide on a convention. So we're going to pick that the normals going outward will be our top, in which case our path still just goes around like that. So that's what we mean by orientable. It means we have to choose a side and stick with that side as being the top. Okay, in which case then our curve then can be defined as having what we call a natural orientation to it, which we'll still call C. So now we're in 3 dimensions. We have this surface attached to our curve. All right. So in a sense that C is the boundary of our surface S. Okay. All right. So with those details aside, we still assume that this is going to again be continuously differentiable. We want P, Q, and R all their partial derivatives to be smooth. We need to be able to integrate them. So what we write down then again is the work integral over our boundary C against the force field pushed along on this path R, and that's going to be equal to now the surface integral of the curl of F, dotted with n, the normal vector, which we've defined here as being outward of the surface, ds. Okay, so each little patch there. All right, recall what the curl is again. That's going to be the del operator crossed with our vector field. Okay, so one might want to ask then why, and recall then that the curl, just to get a sense for what this is. Remember, this is I, J, K, the partial with respect to x, partial with respect to y, partial with respect to z, and our vector field functions p, q, and r, and that becomes we can see this easily as ry minus qz, comma pz minus rx, comma, and then finally qx minus py. Those are the 3 components of our curl, and you notice that the last component, qx minus py, is precisely what we observe in Green's theorem. And so we see that there's definitely a pedigree here, that this really is a generalization. We've just had to add more dimensions to our integral on the right-hand side. We're still integrating over a 2-dimensional object, but now that 2-dimensional object is a surface embedded in 3 dimensions. So we want to get some idea, again, why. Why does this theorem work? So we're not going to give a direct proof, but rather appeal to some knowledge we have about the curl and some knowledge we have about work, and use that to understand what's going on here. So let's get a new sheet of paper. So again, I'm going to take that surface we had. I'm going to put it right here, front and center here. So I'm going to tilt that surface over on its side a little bit. Okay, so we're going to tilt that on its side again. And again, we're going to keep with that same orientation. We're going to have a work integral against that force field going around like so. I'm going to draw that surface again, like that. Okay, so here's our surface. It's a little off kilt. I'm going to try that again. There we go. All right. And here's our surface, and so here's S, and there's our boundary to the surface, which is this little curve going around as such. All right, and so now we have to probably use a little color coding here. So I'm gonna because we have a lot of things going on. First, we have F. So that's a vector field, but we're going to color code that to be red vectors, okay? And then we also have the path C, which I'm just going to, that's going to be for R, and it's also going to be for R prime, which are exactly these right here. That's what these black arrows are. So we'll leave that in black. And any other kind of boundary or edge of something of our drawing, we'll always put those in black. Likewise, we have our normal vector. So I'm going to draw a little patch on here of our surface, like such. Get it looking good. And we have to draw a normal vector. And I'm going to indicate the normal vector by a blue arrow. And so we'll draw that right on there. So I'm going to draw that to be our normal vector. And again, this is of unit length. Okay, we'll think that is unit length of 1, right? Okay. The norm, or the length of that vector, is 1. And then finally, we have to indicate the curl vector of f. I'm going to indicate that with the green arrow. All right. So our vector field f, we'll put that on there, and we'll just, and again, this is all arbitrary. I want to indicate it with artwork and just make more sense to everybody. So that'll be f. Likewise, the curl vector field, which is it's related to f through that curl operator that we just talked about, but it's altogether could be pointing in a different direction. So I'll just put it like that. So that'll be our curl of f, which again is the del operator crossed with f. Okay, and that'll be pointing in a different direction, and in general there'll be some angle between them. Not so we'll let that sit. And then we also have to, and now what I'm going to do is indicate what do we know about the curl vector. We've talked about the curl before. So in general, the curl of any vector field, it indicates an axis, which we'll just put like that right there. And it indicates also a little patch of plane. It's an axis where the circulation of f, the original vector field, is maximal. It's like the maximal swirl around this. So we think of this as being as swirling around like such. Okay. So in general, though, our patch of surface may not be on the same exact. It may not be on our same exact plane. It might be a little off like that. And again, we indicate that the normal to our surface is being right here, and the arrow there. So there'll be a little off, right? And so, of course, let's now compute a work integral going around this little patch. And I've indicated on our surface here as such. It's going around like that. Okay, again, and so we know that what we know then is that the curl, if we take this little work integral, and I'm going to call this Wi, and I'm going to call this Ci, and I'm going to call this patch, actually I'm going to call it delta S, C delta S of I. I'm going to call this little patch here as a delta S. That's a tiny little patch of surface. And again, we'll put there, I'll call that delta S. All right, this is just a blown up version of it. And that's going to be equal to the integral over the path around delta S of our f dot dr. And what we have to do then is equate this to, so we know that the curl, the curl vector where it's pointing, the green arrow, that's the path where we have maximal circulation. We may not have maximal circulation along the black path, but it's close. So the idea is that we want to get the component of the curl vector that we can that measures that circulation around this point that's indicated right here, right? So it turns out we can write this down. Is that going to be the curl of f dotted with n? Because again, the dot product always measures the component of the curl in the direction of n, all right? And then what we have to do is make that representative, call that delta s, okay? So now what I want to do then is we want to now make a patchwork of other little curls and other little work integrals all around here. We want to tile out the entire surface. And I'm going to do my best artwork here to fill out this patchwork. Like so. And of course we also go around the back side like such. And recall then, so at every point, I'll use that as a representative point. We'll think as that as a patchwork that creates our surface integral. Those are our representative points. And we're going to compute a bunch of work integrals all around these little, each is a small patch, delta S I, which is surrounded by what I'll call C delta Si. Okay? So each one of those is going around like such. So what I want to do then, so that allows us to compute a surface integral. And we have all these little patches to do. So we're computing all these little work integrals. And so notice one thing, that if I have two squares like this, if I want to do two work integrals, I'll call that, and we're going to do them in that counterclockwise orientation. I'm going to call this path C1 and this path C2. And so when we go around, though, the boundary between the two, so if I want to compute this work integral here as C1, call that W1, it's going to be dr. And then I want to calculate also work 2, C2, f.dr. Okay, these two work integrals, but we see that they share a boundary here where we have opposite paths going there. So at the boundary, we see the work that you go this way and you go that way will cancel, and that's erased. We can call the big path, we'll call that C3, and the sum of both of those will equal integral over, pardon me, I'm going to change my notation here, over C3 of f.dr. And C3, of course, is equal to the union C of C2 and C1, but we have to subtract off what I'll call C shared. So every boundary point will get canceled. And we notice here that if we do all these work integrals here, anytime they share a boundary, they cancel. And so every boundary point on every work integral will all cancel. All right, so we can formalize this process. All right, so if this was the work from one tiny patch, what we can do then is say, we can write it down now as so far. So we can write down the sum of all the work integrals, wi, I equals 1 to n, and that n will just cover the entire plane, or the entire surface. And we know we can write that down as the sum of I equals 1 to n, the sum of C delta S I f dot dr. And we know that as long as all these patches are small enough, we can approximate that by a curl times this tiny patch there. Dotted with n times delta Si. And that But we notice here, so this of course is approximately the integral over our surface of the curl of f dotted with n, the normal, outward normal to our surface, ds. But we know here that every boundary cancels on all the interior boundaries here. So what is left after all of them cancel? If every shared boundary we have to subtract off, what's left? Well, the only thing left is the boundary of the entire surface, which doesn't share any neighbors to its right side there. So what we get then is that has to be equal to the outer boundary of the entire thing, which is f dot dr, which we call capital C. So these two things are equal. And that gives you a good idea then of what's going on with Stokes' theorem. Okay, so again, we can write those as equal to each other. All right, so again, what we have is this mass cancellation. So this is very nice. So there's our theorem. We've learned a way to understand what's going on here. So what we want to do now is just talk about an example. We'll do one example real quick. So this is number 16 from the book, and we're going to write it down. And number 16 is a bit conceptual. So the vector field involved is z, negative 2x, and 3y. So that's our vector field. And now what I'm going to do, and it doesn't give you a surface, but it does say that we're going to let C be any closed curve, simple curve, in the plane x plus y plus z is equal to 1. So what does this look like? That is our z coordinate. There will be our x, and that'll be our y. And that plane intersects at x equals 1, y equals 1, and z equals 1, where all the others are respectively 0 for each of those 3 dimensions. So in the first octant, the plane intersects these points like such. So of course it goes out beyond this. It keeps going. But let's confine ourselves to thinking about any kind of closed curve here, like that, like such. All right, so so we know then that if I want to calculate any c in here, we have this work integral we got to compute, dr. All right, so it hasn't. So what is the goal of the problem? The goal was to show that this work integral, it depends only on the area enclosed by C. So I'll put A in there, all that area there. Okay, so let's show that's true, and we're going to use Stokes' theorem. So what we know about Stokes' theorem is that as long as we have that as our pathway in space, any surface that we attach to it, going front or back or whatever, it doesn't matter. It's all the flux through that, the flux of the curl vector through that surface is what we can compute, and it will be equal to the work integral. All right. So let's compute the curl. So of course we need to say this. So for whatever it is, we know this is true about Stokes' theorem. We can write it down that it's equal to some surface where this is the boundary of the surface. That C curve here is the boundary of the surface. equal to the curl of f dot n dA. So that could be any surface. Okay, so if it's true for any surface, then it should be true for a surface. So it should be true then for surfaces in plane x plus y plus z equals 1. So it should be true for this surface that's actually in the plane defined here. And we know the normal to that surface is going to be the normal 1, 1, 1. Okay, so now we have a vector coming out of there. We'll call that n. All right, so what we have to do now is I'm going to get a new sheet of paper out. N again was 1, 1, 1. And our vector field was z, negative 2x, and 3y. So we need to calculate that curl vector. And that's going to be I, j, k. It's the determinant of I, j, k, partial x, partial z, y, partial z of z, negative 2x, 3y. Okay, so we can compute that to be, you can compute that to be 3, 1, negative 2. Okay, so, and that's pretty simple to compute. So it turns out that this is a constant rotation, constant rotation vector field. Okay. All right. So we know that any surface integral we compute, we're going to take our surface then to have a normal n equals 1, 1, 1. So our curl integral dotted with n times ds over our surface will then reduce to the curl vector dotted with 1, 1, 1 ds, and we can compute that to be 3 plus 1 minus 2, and that's going to be 2 ds, 2 s ds. Okay, so here that vector, of course, is just going to be equal to area. So it's going to be 2 times the area of enclosed area of C. Okay, so we'll remember what the closed area of C is. We have Z, we have our X, we have our Y, and we had that plane that's sitting in there. We had some path in there, and the area inside was this. And so yes, the work integral that we do, the work is going, the work over our path of our vector field dot dr is going to be equal to 2 times the area enclosed by C. Let's put that in quotes. All right, so that's a nice result from Stokes' theorem. So thanks very much.